right now. So so the talk and the meeting is being recorded, and if you would rather not be recorded, then just turn your camera off and use the chat to ask questions. So we will take questions after each talk, and you can either put them in the chat or just raise your hand and ask them directly. So this is the last day of this Newton Institute workshop on verified software tools and experiments, but we have some celebrities talking today. And so the first one is, I need to dismiss some windows here. So our first speaker is Lenore Zuck from the University of Illinois at Chicago. And well, I'm not sure she needs much of an introduction. Well, certainly I was, in my own work on compiler verification, I was greatly inspired by her work on translation validation and the TVOC system. That she's done a lot of other kind of work in software verification. And so today she's going to advocate for a teaspoon of formal methods instead of maybe a full cup or two. Thank you, Lenore.
Thank you. What a wonderful introduction. I should nominate to be my introducer. So Shankar's mandate for the talk was, at least to me, addressing the challenges of creating robust, scalable, and usable tools and a tool infrastructure for the analysis, verification, and synthesis of software. Of course, I couldn't do it all, and each of us took whatever we wanted. I wanted to focus a bit more of what scalable means to me, and what does it take to create usable tools and for analysis and verification, and I'm talking small v verification, not a big full verification, which I think is what we need in lots of things. So where do I come from? Oh, I forgot. I come from Lincoln Park, and since Nate gave pictures yesterday, I want to compete with him. But then my dog heard that this talk is recorded, and she said she's got to be part of something because she's just been testing things. So here she is in the lily pond in Lincoln Park. So for me, the notion of scalable is more about the science of using science. How to make optimal use of what we know or the tools we have in our discipline. So we talk a lot about scaling in size. We do that a lot. We do a really good job. We go from 100 variables to 100,000 variables. But I think we need also to focus on scaling in the target of applications to find larger markets and settings for the things we do. And I'm going to give 2 examples of things I have been involved with that are along this line, and what, at least from this very narrow standpoint, what were my conclusions. So I'm going to start with translation validation, and the vision was from Emil Noeli that he was involved in some European project, and they wanted, and SNECMA wanted to make sure that everything is fully verified, and there was an issue of translating from Ada into, I don't remember the name of the language, and they wanted to verify the translator. His insight was that validating the translator is verifying the translator is a very big job. Moreover, once you validate a translator, you need to freeze it. So instead, we can verify each run of the translator. The advantage would be that you can continue developing the translator. It's going to be cheap. And it also would provide for independent cross-checks. Of course, the disadvantage is that will be additional cost for each one. But as experience has taught us, it's not a lot. It's well worth it. In the very high level, we have a source, let's say S, a target, say T, and great names. And we assume that they're both in a language that we can create semantics mapping. So we will be working on the semantics of S and the semantics of T. And to show that T is really a good translation of S, we create a refinement mapping such that everything that T produces can be produced by S. And this is the general idea of translation validation in its various forms. It's been mainly applied to optimizing compilers. There, it's trying to go very high level, more or less the recipe to do that is that you express the source and the target as a control flow graph. You find a cut set point that is a set of points in both source or target that includes the initial location, the termination location, assume one termination, and includes at least one node from each loop. So then you create a data mapping that kind of looks like, under certain conditions, this variable of the source is expression of the variables of the target. You create control mapping from those points you selected in the target to the points you selected in the source. I put it in a different color, which happens to be red, no meaning to the red, generating variance for each basic block. And the reason that I colored it, sometimes it's done and sometimes it isn't. And you identify a verification condition for each simple target path. That is a path between two of those selected target nodes that doesn't pass any other. Then you validate the verification condition using SMT solvers. So if you do include invariance, you just get more power for some non-structure preserving transformation. Later, there was a need for some meta rules, for example, for loop optimizations that depend on affine transformation. And as Kedar and I later found out, for interprocedural optimization, it really helps to have meta rules. So you can have a bunch of stuff on the side. And we have, with Kedar, a more contemporary version where we annotate the optimization and generate witnesses, and we have a new idea of shadowing, and all this makes this verification conditions, their generation and their checking simpler. It's all small variants on the same theme. But the real work is in static analysis, which is, I consider, extremely light formal methods. The framework itself is where you have more formal methods, and the framework itself is very sensitive. Even the shape of the verification conditions depend on which solver you're using. But when you go and apply it, the real work is in static analysis and in having students chase all the optimizations. Right now we're working on LLVM. I'm sure Javier can have his own experience of where the work is, but we're not really fully verifying it. So was it a good 4 minutes? This is like university tools that become obsolete because whenever, like, we started with the Open Research Compiler and the closed it, we went through many compilers since then. And I'm not sure that there's anything that is really running right now as we speak. But there was actually a use for it. And that goes way back. And I was spending some summers in Intel consulting in the formal verification group, and Moshe Vardi was actually in a different group, that is equivalent checking group. And they had this problem that Intel develops chips, and there's Pentium 4 and 5 and whatever, but in between each two major progress, like two Pentiums, there are mini micro changes. They add a cache line, for example. So each of those small changes is accompanied by software that utilizes this little enhancement. And it's impossible for them to keep software for each of those successive changes and to deliver the right software updates to each of to wherever those chips are. So rather what they do is that when they improve the software, when they use the new functionality, they say, hey, but for the old software, just don't use it. And then comes the issue of backward compatibility. They want to make sure that the new software working on the new CPU will work on the old CPU the way the old software did. And this is their backward compatibility. And they hired me to create translation validation for that. this is not exactly the framework that we're working on. Those microprograms are very low-level, machine-oriented, sequential control flow. Sometimes they're executed out of order. Each of them implements a single macro instructions and registers, and they do it by means of micro instructions, which are called UOPs. And abnormal termination is something that is very common. It needs to be dealt with very explicitly. So those UOPs are 3 address operations. They interact with the hardware. They have jumps like gotos, which can be either internal, external, or indirect. That is computed only at runtime. The target address is only computed at runtime. So we model it with its own intermediate representation language. I'm sure it had a name, where, of course, the first class citizens are bits and bits vectors because our working registers. There are conditional assignments and gotos and all that. Each UOP is implemented by a template, and I'll soon give you an example that has a signature and a body. But what's new that there is a very explicit treatment of side effects. And each of those successive improvements in the microarchitecture each has its own template file. So here is an example. It's not perfectly typeset. Here is a flow. So let's say that the register 1 gets the content of register of the address at register 2 with the offset at register 3, and in register 4 you add register 1 and register 5. It's just an example. So we need to expand. What does it mean to do the memory read? And that's in purple. And what does it mean to do the addition? And that's in blue. And you can read all this, but let me just point you to the interesting thing. In line 3, after you add the register to figure out the address, you need to exit with address overflow. So that's a special exit with an overflow. And you need to send something, some values to this exit. Also in line 5, this is something that they do in microcode, that is whenever a register it gets 0, some 0 flag, some system flag is raised. And you can see that this is in the add. And if you notice that I didn't include the integer overflow in the add, that's because I wanted it all to fit into one slide. So assume we don't have that. So this is a way you can expand. You can have those templates for each of those UOPs, and you can expand them. How do you create them? Well, you need the microcoders to create them because it's very difficult to tell. It's two things here, of course. This is microcode, so they'll never share it with us. In spite of all the DNAs, they will not share the microcode with anyone. And it's really good because then the burden on actually expanding the macrocode to templates is on them and not on us. But there are other little things that came in the way of the modeling. Microcode is an open system. We're used to closed systems. We always try to model things in closed system. And here we have a lot of environment interaction. Then there are out of order execution, they're restricted out of order, but there still are. As I said, there's not a single exit. You can exit a program in different ways, which we call doors. And in each of those doors, you need to assign, there are different set of interesting things for that door. Also, the notion of equivalence to say that this is run exactly like it ran on the old machine needs some massaging. This is not the same. The environment is not the same. It's not even clear what to say that it runs the same way, because the same is not the same. And of course, once we created symbolic paths and ran them to SMT solvers, but there are often too many symbolic paths. Just think about it. If you have a program that just does if then else, if then else, if then else, you got exponentially many paths. So that would choke the validation process. So we needed to do some optimizations. I don't know, well, we don't have time. My favorite one is something called pruning, but we'll forget. And the thing, it worked. What I mean it worked, they found bugs. And they found bugs, and the microcoders loved it, and they kept on using it. And it was a great success. So I'll switch to a story which, at least at that point, doesn't have much success. And this is internet protocols. Internet protocols are written in RFCs that are written in English, and it could have been any other natural language. Okay, Shankar would correct me. Maybe Sanskrit would have been really good for this. And they're guidance for implementers. They're guidance. They're not even very exact. They're ambiguous. They're contradictory. They're a mess. And what happens then? Independent implementers implement them, and then they go and test them for interoperability. Of course, those interoperability, which are called interop, and it's less of a mouthful, they don't, even if those things interoperate, they don't represent the full behavior that is allowed in the specification in those documents. Of course, they do any compliance check. You can't guarantee that it will interoperate with future implementations. This thing led to security bugs and some other problems. But what I found is the scariest, that eventually those implementations become the de facto standard. If you want to implement a new protocol, you need to go and make sure that it interoperates with the old ones. So this is work with Ken Macmillan. We thought about the network-centric compositional testing, which is called NCT for this purpose, which is again a teaspoon of formal methods. It's just really not a lot. And the idea is that we will manually, blood, sweat, and tears, it's really hard, create formal specification of on-the-wire behavior. What I mean on the wire is as an observer would see the traffic, which is not what's really in the RFCs. You need to extract it. Then using randomized constraint solving and SMT solver, we'll get randomized automated tests for implementation. So this acted really good because the randomization acted as an adversary. And of course, we found mistakes in our specification and we had to refine the specification, but we also found lots of ambiguities in the RFCs, and both implementations and the RFC were corrected accordingly. And this test allowed actually to check implementations for compliance. So what's compositional about it? So we make the assumption of input of one processor treated as guarantees to the output of the other, the usual way. Here, usually processes are client and server, but I'm just saying usually because we have some flexibility to define our processes. So here is the traditional compositional rule that assume P, M1 guarantees Q, and assuming Q, M2 guarantees R. So the parallel composition of M1 and M2 will guarantee R, assuming P. The point is that this parallel composition establishes an implicit channel between M1 and M2. And Q is a fact about something that is happening in the channel. But the role of Internet Protocol is to create this channel. Those channels are not given. We can't assume anything about those channels. There is no one-to-one correspondence between processes and addresses. The protocols are specified in terms of transmissions, not in terms of processes. So we can't apply the rule, and we have to come with a compositional rule that will fit the circumstances. How am I doing with time?
Well, you have maybe 4 or 5 minutes to finish, and then we'll switch to questions. Thank you.
Okay, thanks. I just wanted to know. So we came with a rule that depends on backward assumptions and some global specification. The gist of the rule was that each process guarantees the specification, assuming the others did not violate it. And that really means that the earliest violation cannot be the process's fault, and therefore there is no earlier violation. So this is the proof rule. And I'm just skipping that there was another issue of the package being too long. and taking too long time to generate them for Z3. So we did something that we call dependent field extraction, realizing later that it's used for a totally different thing in a totally different computer science area. But the idea is to try to separate the constraint, to try to solve as much as possible locally, and then combine the stuff, and that created great things. And I'm skipping it. And then we applied it to Quick, which is a new protocol. It's been for 5 years, 4 years now, going under RFC revisions. Of course, they want to do everything better, reduce latency, do better congestion control, do everything better. And it's a lot of the internet is now running on Quick. But the standardization, when we started working, was in version 7. I think that we got our results, what about version 12? Now it's version 34, draft 34, that is also been renamed RFC 9000. And the draft specification is very problematic. So we wrote specs in IB only for a partial set of Quick because we didn't need to do everything. But for some things, we didn't do the specification. We rather restricted and did real implementations. For example, TLS 1.3. Nobody has the specifications. And it will be it's a project harder than specifying Quick to go to TLS 1.3. So we just took an implementation, of course, by virtue of that restricting the behavior we got. And we applied it, and we found bugs, and most of them were new at the time, and some exposed security vulnerability, which was sweet. So there was an issue of client migration, and the client kept migrating from one address to another, and the server could not keep up where the client is. Then what really, the reason we found it is because we only allowed 2 addresses for the client. So the randomized testing kept flipping between those 2 addresses when we tried to check the migration. But what it actually exposed is a DOS vulnerability. And indeed, when I looked recently on the document, they do have what I think is an explicit treatment of that, to say the server stop sending too many things, because that will expose you. Actually, the group at ITF were very responsive to the things we sent them. They're very excited, and they wanted us to do more and more and more of it. Several of them even seemed interested in doing it themselves, but I'm not sure that anybody did, because I haven't heard about it. There is a group in Galwad that is interested. But I think that the message you're trying to convey is, hey, those documents that you write only are providing guidance for implementation, but you're totally ignoring what does it take for implementation to be correct. We want the on-the-wire behavior to be given by the ITF, not by us. It's not a job for academics to do. And okay, so the takeaway. We don't need a lot of formal methods to make difference, to get really better results in different areas. We do have a major hurdle, and this is language. So whether it's microcode that we're not allowed to see and cannot understand, or whether it's RFC documentation that it's kind of a natural language, and I say kind of because it doesn't have even have the usual semantics. There are musts and should and all that. It's not like the way we're used to. But I found that the impact is direct proportions to how much the audience has an express need for the work. So if I go back to this science of using science, it's just mainly about medical experimentations and psychological and medical experimentation. They ask, do the research results scale to larger markets and settings? And I think for us, it's again the scalability in the application domains. So which application domains can benefit from our methods? Then they ask, when we scale to broader and larger, again, what I commented out, or medical specific, should we expect the same level of efficacy? And I'm going back to what Amir asked in this very first meeting about usable verification. Tucker, you may remember that somewhere in the South, Charlottesville or something. And there he said, you know, it's okay to do small, like little v verification if we can make it more usable and that more people could actually use it, giving up precision, that's okay. And the third question to ask, and I have no answer to, is what are the important threats to scalability? And I have no answer to that. So I think that's my last slide. So thank you, and I hope I made it in time. Yes, it is.
Thanks a lot, Lenore. That was a nice conclusion slide. Do we have questions? Well, I'm not seeing any raised hands or anything in the chat, but I hope. Yeah, I'm using the web client. Oh, yeah. So Supratik, you'll please ask your question.
Yeah, hi, thanks, Lenore. Great talk. I had a couple of questions. So the first is, you mentioned about randomized constraint solving for generating the tests. So I was wondering what tools are used for that purpose, because most state-of-the-art constraint solvers, they zoom down into some corners of the solution space. So I guess they will not give you random.
What of the space? I missed words.
I mean, the efficiency of most modern SMT solvers, for example, is because they can zoom down into some parts of the solution space and prune out large parts of the solution space. So their solutions are not going to be random. They're going to be biased in some sense, right?
Yeah, okay, so the random is not random. The random is not, we don't know the distribution. It's kind of used Monte Carlo. But actually to pin down the distribution is a lot of work, and it's not clear it's worth it.
Yeah, I mean, that's the hard problem too. I mean, we've done a little bit of work on that, but generating solutions which are uniformly randomly distributed or almost uniformly randomly distributed, it's a much harder problem than just generating a solution.
Yes, and it wasn't worth it. You see, we got the bugs and we got the experiment working without worrying too much about the
randomization.
Okay. So yeah, we're fully aware we don't know it's a mystery random distribution.
Yeah. Okay. The second question I had was, when you talked about translation validation, it's beautiful work that you have. I mean, there are instances where the language standard keeps things undefined, right? It says that for some programs, the behavior is undefined. And I was wondering, how do you deal with that in your formulation of translation validation?
I personally don't, but I know people who do. And,
okay.
And so things like this, the microcode is pretty good example of you can get into gory details. You choose the level of details. We always choose how far we go, right? So in most of the work about translation validation, we assumed we ignored exceptions. We ignored, think about an optimization, for example, that you have a line that says X gets X over 0, and then X is never used. So many static analyzers will take this assignment out because X is never used, so we don't need the assignment, right? This definition is not used. But in fact, you just take the semantics of the program, you change it from an exceptional exit on 0 divide to 1 without. So it's always how far do you go? And in microcode, you really go to the gory details. And in most of the work I've been involved with, you ignore the gory details and choose your poison. And it's also how far do you want to go?
Yeah. I guess it depends on, how much of, as you said, how much of precision you want to keep, and perhaps, being too precise is not necessarily what we want in a practical application. We just want to.
It depends also on these turtles all the way down.
Okay. Thanks.
If I can add something, and actually Sanjiva Prasad is commenting in the chat similarly. Yeah, it's actually better sometimes to underspecify and leaves areas completely non-deterministically open and to do things like transfusion validation. Do we have other questions? You can just speak. I'm not seeing any hands raised. But yeah, please. Speak.
I had a question, and I was wondering whether anybody has some suggestion for answer. What are the threats we're facing to scalability?
Well, I'm afraid we would need like a couple of hours to really discuss that. So, so maybe Benjamin can start to set up.